we covered in George 1 showed that the light-sensing molecule is a protein, so-called opsin, which is covalently bound to a chromophore 11-cis retinal, shown here, the covalent attachment to the amino group of the lysine. And the effective light is to isomerize this double bond from cis to trans. That's the stimulating event in the vision. And now, fast forward another 30 years, at this point, molecular genetics arrived on the scene, and I was fortunate to be in the right place at the right time at Stanford University in the 80s, early 80s, and picked up this problem and identified and sequenced the genes for the human visual pigments. And we have 4 light-sensing proteins. Each binds 11-cis retinal, and each has the same overall 7 transmembrane topography. There are 2 protein-coupled receptors. And in this pairwise comparison, we see the short wavelength sensor, so-called S, versus rhodopsin, the one that mediates dim light vision, where every filled ball indicates an amino acid difference. And here is the medium wave sensor in the medium wave cones versus rhodopsin. Here's the medium wave sensor versus the short wave sensor, so we have 3 cone sensors, 1 rod sensor. And then here, the medium versus the long wave sensor. So in just looking at the sequences of the 4 receptor proteins, there's an immediate asymmetry here, which I think you can appreciate, and that is that the medium and long wave sensors are much more similar to each other than are any of the other comparisons of the pairs. And that comes out to be reflected in the absorbance spectra of the encoded proteins. So this is work that Shanak Most did when she was a student in the lab. She expressed the proteins in their cloned cDNAs. We constituted each with the chromophore and took the absorbance spectrum in a spectrophotometer. And here is the S, or shortwave sensor, peaking at around 440 nanometers, rhodopsin at about 500, the M, or medium wave sensor at about 530, the long wave sensor, L pigment, at about 560 nanometers. And you can appreciate that the M and L pigments are quite similar in their absorbance spectrum. They all have the same bell-shaped curve, but they're shifted back and forth along the wavelength axis, depending which protein they bind. So just to connect to that observation of Newton, that certain combinations of lights were indistinguishable. Let me just give you Maxwell's explanation for that. Maxwell conceptualized the system in a very simple 3-dimensional format. He suggested that we can just think of the medium wave sensor amplitude of excitation as some value on one axis, the L sensor as another value on the second axis, and the S sensor value on a third axis. And so the color world is basically a 3-dimensional space, which is defined by the degree of excitation of each sensory receptor type, and every stimulus is some point in that 3-dimensional space. So basically, any particular combination of lights which leads to the same degree of excitation, i.e. maps to the same point in that space, will obviously be identical to our percept. If it was the identical percept, it won't necessarily be physically identical. It will just map to the same point. Okay, that's appetizer number 1. Let's move on to appetizer number 2, which is inherited variation in human color vision. This will bear directly on the evolution of color vision in primates. One of the surprises that we got when we identified the DNA segments that encode the human L and M and S pigments is that the L and N pigments are right next to each other. The genes that encode them are right next to each other on the DNA. Here they are in schematic form. 5' is the base of the arrow, 3' is the tip of the arrow. The L pigment is upstream, the N pigment is downstream. And we believe, and I'll justify this in just a few minutes, that they arose by a duplication event in which there was already pre-existing in this species, this ancestor of ours, an L pigment gene and an N pigment gene, and then an erroneous meiotic recombination led to the rearrangement which gave L upstream of N. Now, the genes are still incredibly similar in sequence. This event must have happened not so very long ago. They are about 98% identical at the DNA level. The region that's duplicated is 39,000 bases. And in fact, because of that duplication, there are continuing rearrangements, meiotic recombination events in which duplicated units are offset, and so one gets not just the basic arrangement of 1L and 1N, but 1L and 2Ns, 1L and 3Ns, and even 4 or 5. I was the wild type in these studies. I turned out to have 1L and 2N pigment genes. That's actually the most common arrangement. About 60% of human X chromosomes look like this, about 20% look like this, and the other 20% have additional N pigment genes. One of the most common polymorphisms in our species. And it's just this kind of variation, this unequal recombination, homologous recombination, but offset, that is the source of the genetic mischief that creates the common anomalies of color vision in humans. And the most famous person who had one of these is shown here, John Dalton. Dalton, of course, you know from the unit named after him, the Dalton is the unit of mass in chemistry and physics, was a remarkable intellectual, lived in the late 18th century in England, and in his first paper, written in his late 20s, actually about himself, which he entitled Extraordinary Facts Relating to the Vision of Colors, I tried working in words like this in the paper so as to make it similar for himself. Extraordinary, this and that.